The speedometer of a car doesn't care about whether you're going forwards or backwards. Whichever way you go, the speedometer reading goes up. It's the same with the odometer, which is the display of numbers usually underneath the speedometer. This gives the distance the car has traveled. There's often a total distance the car has gone, like since the very start, and then the distance of the journey, or from whenever it was last reset. Anyway, the odometer doesn't care where the car has gone or whatever direction. Every mile is counted and direction doesn't matter. But what if you're waiting for your Domino's pizza to arrive and you're tracking the delivery guy? Well, in this case, if you think about it, Google Maps is actually giving you two bits of information. The distance away from you, but also the direction from you. In physics, an arrow from the start location to another location, with the arrow showing both distance but also direction, is called a displacement arrow. But what if it's not a Domino's order you're tracking, but an airliner, just like the one you might have flown to Ibiza on, when you had had enough of jigging to Dizzy Rascal at DeVito's, and wanted a club in the sun? This of course happens in the air traffic control tower at airports. It's a live screen showing both the speed of any aircraft nearby, but also their direction, and again, this is shown as an arrow. This speed and direction arrow is called a velocity arrow. Arrows are pretty useful because they show not just size, but also direction. As well as displacement and velocity arrows, there are also force arrows and acceleration arrows. These four arrow types, displacement, velocity, force, and acceleration, are known as vector arrows. The word vector is Latin for carrier. To carry successfully something from one place to another, you need to know the distance and direction your destination is, from your start position. Stuff that isn't shown with an arrow, like distance and speed and everything else basically, is known as a scalar quantity. Dealing with more than one velocity arrow, to find like the overall arrow, is something you do all the time without consciously thinking when you are catching or kicking or heading a ball. You also do the same thing with dealing with displacement arrows, like if you're meeting someone at some location. Although in the real world you often do this adding arrows thing automatically with just years of experience, in physics you need to be able to do it written down for any vector arrow. Here's how we do it. Sassy Sarah moves 40 meters due north from her start position, then 30 meters due east. Find the final displacement arrow from her start point. First of all, work out a scale which will mean your arrows will fit on the page. Here, 1 centimeter equals 10 meters would be sensible. So now we draw an arrow 4 centimeters straight up. Do it neatly and accurately. And then an arrow 3 centimeters east. The final displacement arrow is then drawn from the very start point to the very end point. Measure the length of that final arrow and convert it back using your scale. Use your protractor to find the angle, then make sure this is a bearing. And that's it. You found the final displacement arrow, both the length and the direction. Put the two parts of the final answer together at the bottom and underline it. Although, sometimes, finding the length, otherwise called the magnitude, is part A of a question, and finding the bearing is part B. This time, Dodgy Bob walks 50 meters due east from his start position, and then walks 20 meters due south. Find his final displacement arrow from his start point. So, go through the same process as before. Did you manage it? Good job. What about this one? What would you do? Finally, take a look at this one. Are you getting used to these by now? Well done. Now, what we call instantaneous speed means the speed of something at a particular instant. An instant is a very short moment in time. Traditional speed cameras measure a car's speed during the instant the car passes the camera. Speed is a calculated quantity, and we need a distance and a time, which we can then use to say that speed equals distance divided by time. With instantaneous speed, the distance and the time are very short. With the speed camera, the distance is the short length of white lines you might have seen on the road, just in front of the speed camera. The time value is the time the car takes to cross those white lines. Then the camera does the calculation speed equals distance divided by time. The problem with traditional speed cameras is that cars tend to slow down for them, then immediately accelerate away afterwards, back to their old too fast speed. So average speed cameras use a much longer distance, like a kilometer or two. The time measurement used is the time it takes the car to travel this whole length. The timer starts when the car passes the first camera and stops when the car passes the second camera. In this way, the car has to be driven at the right speed along the whole kilometer or two. Otherwise, the average speed will become greater than the speed limit, and the driver will get a speeding fine. This experiment is like a model of the two kinds of speed cameras. To find the instantaneous speed of the trolley thing as it passes point Y, the distance measurement we use is the length of the card on the top of the trolley, and the time measurement we use is the time through the light gate at position Y. To find the average speed of the trolley, the distance measurement we use is the whole distance between positions X and Y, and the time measurement we use is the time of that whole journey, between positions X and Y. But for both instantaneous and average speed, we use the formula, speed equals distance divided by time.